Okay. All right. Oh, sorry. Should I be here or?
She wants in the middle.
Yeah. Yeah, it's, I can take a look at this. Yeah. Yeah. Put here instead. Okay. Yeah. Thanks for people coming here for the rather technical talk about pure functional solidity for fine profit. I just wonder, like, how many people are actually familiar with the idea of functional programming, just so that I know. All right, great. So let's just get going. So the goal of this talk is to demonstrate the possibility of limited functional programming in Solidity. And the second is I use a new paradigm to build a simple super token step by step. So it's going to be involved, and I'll try to go right speed, but it's a bit short time. The third one is examples of using Setora to formally verify the code. Right? I don't say it's a complete down, but just exploring the possibilities. And last, if you are not familiar with the functional programming yet, it's to make you interested in functional programming in general. Right? So okay, so let's start with today's task or idea is let's reimagine what is a token, right? So let's have a new mental model of what is a token. Let's call it super token for now, right? So token is like a bank containing a collection of accounts, right? That's how we know about even ERC20 tokens, right? Each account has an owner, representing the owner's wallet with a collection of, let's give an abstract name, monetary units, not to be confused with currency units. We're talking about just abstract units, right? So, and these monetary units provides a balance, right? And a set of payment primitives, right? So let's have this mental model and move on and see what's it about, right? So what are payment primitives, right? Let's give 4 of them, and they have 2 dimensions. One is one-to-one transfer, one is instant versus a constant flow, right? So we're all familiar with one-to-one instant, that's ERC20 transfer, right? That's just one thing in that 2x2 boxes. The other is one-to-n instant to all the accounts. There are a lot of ad hoc projects that are doing that, but let's say, can we generalize as sort of a payment primitive? So we want to do one-to-n instant transfer. The other is one-to-one constant flow of money, right? Often known as money streaming by people, right? And the last is the one-to-n constant flow. How about I distribute to any number of people as flow of money, right? So that's so-called a generalized payment flow, a generalized payment primitives, right? Okay. Furthermore, what come with this generalized payment primitives and the new mental model, right? So it's also frictionless. What does it mean? So it's real time. So it's a model that continues in time, right? So it's, in effect, because blockchain move per block, so actually it is move per block, but it's modeled continuous in time. So it's real time, true real time, right? The other is composable, right? So it can be chained with other payment primitives. So the moment you receive the money is the moment you can use the money, right? So it's frictionless in that sense. You don't need to wait for the money to accumulate and you transfer as a batch later, right? So it's using at the same time you receive, right? So programmability also, right? So there's 2 programmability. One is on-chain mechanism, right? So let's say include a callback. So when you receive the money, you act on it. One of the examples is ERC 777. But you can generalize it. If you receive a flow of money, then you trigger a callback, it does something. That's kind of on-chain mechanism. There are certain things you cannot do on-chain, such as reacting on time, right? You can't do that on EVM yet, right? So when the certain time hits, you do something, for example, right? So it's not doable. So you have to provide off-chain incentive when in that kind of cases, right? So a little bit more thoughts about super token before we move on actually about the main topic, which is functional programming, is monetary units. You can think of as coins, cards, or nodes in your wallets, right? So optionally, you can think of like UTXO-based system or on-chain representation of account could be kind of complete bypass. It's no longer wallet, but just a bunch of nodes. You can do that in your UI instead. All right. Okay, let's now have this mental model in mind, and let's build it using Solidity, right? So, but we'll not do all the features we talked about so far. We'll talk about only creating those payment primitives. Also for fun, disclaimer, this is not for production, right? So just for fun, right? So first of all, let's define some types, right? So there's something called custom types already in Solidity. I don't know if you start to use it or not, right? So this is what you can use for wrapping numerical types. And from 8.19, there is something called operator overloading also. So you can actually make it more convenient to use by using that. So let's see an example, right? So first of all, let's define something called time. In this case, the time is int32 unsigned, and you define two functions, pure functions for add and subtraction. And the last line is the 8.19 new feature, right? You can do operator overloading where you say, okay, you say the plus operator is using this function and the minus, the subtraction operator is using this function. So this is the new syntax available from 8.19. So with this, you can then actually use the custom types in a more ergonomic way, right? It's just syntax sugar, but it's rather convenient, right? Let's define more types, right? So you need to have value. Unlike the ERC20 value, this is assigned also, right? So there's a positive and negative, so it's int 256. Similarly, you define the add and sub, and you apply the operator overloading also, right? So now there's flow rate. In this case, let's say it's 128 bits instead, because otherwise, it's gonna overflow. There's only 256 otherwise, right? So very similar code than previous one. Let's move on quickly. Unit. We'll talk about what is unit later. It's really about distribution. Think of the dividends payments. You need to have a share number. In traditional, like how many shares you have, Microsoft share, Twilio share, whichever, and those are measured by something called unit. So this is the type gonna be handy later. All right, so however, Solidity doesn't have a operator overloading when you have two types that are different. So you kind of have to go back to the old way using a library. Say, if you want to multiply the flow rate by time, you put that as a library function, and then you use kind of keyword using this library for the flow rate globally, right? This way you can then have a operator by name of a .Miao, right? So multiplication. So this is you can't do mixed type, so unfortunately you have to do this. All right. So next step, let's define what is actually the thing we're talking about here, right? So we need some sort of a data type for doing this very specific magical token, right? So there are three things. There's a time for that data structure. It's a very abstract name. It's called a basic particle. We will see later why. And there's value and there's a flow rate. With three fields, you can count. Okay, before I go further, right? So there's something in the Solidity about pure, functional programming is that it is not really pure function. Why? Because it's similar to JavaScript or some of the language that when you have an input of the memory data type, storage indicator, you can actually modify the input, right? So this is not really a pure function in that sense. If you know what is actually the pure function, you can modify the input, which is kind of bad, right? So for the functional programming perspective. So what you really need to do is do a clone. So whatever input you receive, you clone it. So you make sure that you don't modify the input. So we keep that pattern throughout the code, right? So make it purer. All right. I need to check the time, so I'm gonna move on fairly quickly. So now we have a small data type. Now we need to calculate the the balance from the data type, right? So it's very straightforward. It's a one-liner. Say, okay, flow rate multiplied by the delta of the time, right? Then you plus something called a settled value. Then effectively you have a calculation of what's the balance of that data structure, right? So it's called a RTB, right? A real-time balance. Another very abstract function called settle is because it's a very important kind of construct throughout the code in order to make sure that when you do operation between two data structure, they are synchronized with the same data structure, same time, right? You settle at the same time. Otherwise, they're not compatible, let's say, or another way to put it. If they're not settled at the same time, you cannot do operation on top of it. So let's call it settle, right? As you can see, first operator is always .clone, so you don't modify the input data, or talking about functional programming, you always clone it. In Solidity, unfortunately, you have to do that, so that makes a little bit boilerplate, but not too much, right? You clone the data, you calculate the real-time balance, it's the second line of the function, calculate the balance, settle it, and put the time in the third field, right? So, okay, now go to the third step, right? One of the things about functional programming is that you define a bunch of functions, but how do you know if those functions are correct, right? So you do now need to define some laws for it, right? So laws, what are the laws, right? So laws like mathematical laws, right? So let's define something called a monoid. If you're in a functional program, you probably know what I'm talking about here, but it's actually a very simple concept. So it's the data structure we talked about there has additional operator, let's call it x, or has some name called append, and satisfy certain laws. What are laws? It's very simple, right? So there's empty elements multiplied by any number, any data is equal to that data. It's like 0 plus x equal to x, or 1 multiplied by x equal to x. You can do different order, left or right, so you can have left and right. So now we have a foundry-based property-based testing, right? So you have any random input, and you test if the law satisfies with any order you have, right? So multiply by append from the left or append from the right, you get the same equality, right? So that's kind of foundry-based testing, right? So the fuzzing to test this law. There's other way to test, but this is one convenient way. All right, now there is associativity, right? So you A multiplied by B multiplied C equal to A multiplied by B multiplied by C with the different brackets locations. And in the foundry is also a very clear one-liner, right? So you check if it gives the same data, you do kind of with different brackets applied to the data structure, right? So it's very easy to test, right? So that's a common mathematical property for the data, for a lot of data, especially for data wants to append to each other. But the data we just defined also has its own laws, right? Because we were talking about some domain-specific stuff. Something is called, there's a settle function, right? So if you settle twice, they should give the same result, right? So it's kind of idempotence, let's call it, right? So actually, the fun fact, I asked ChatGPT, can ChatGPT generate the function if I just give the function name? Actually, it generates pretty okay. I mean, it doesn't work fully, but it does understand the word and it understands what it means, right? So because in principle, it's a second formula is just settle twice with the same time is equal to settle only one time, right? So that's basically what about. This is not very interesting yet. The next interesting one is what actually about the constant flow of money, right? So you actually then test the real-time balance is always the same no matter how you settle it, right? You have 3 timestamps here now in the foundry-based testing. You have T1, T2, T3, and you settle with a different order. Then you calculate the balance at the same time. They always equal. Right? This way, you can make sure that the function you define actually makes sense according to this law. Right? So Foundry, again, provides a very nice facility for testing this. It's a very concise test. You just test the property, and you put random inputs, and it will give you 1,000 data points, and it all works. Then you're happy. Right? So, all right, I'm going to speed run now. The number 4 step. We talked about 1 to n also, right? How do we model the 1 to n? Now we need a new data type, right? Now let's call it the pool of money, right? Let's look at the pie chart. Imagine, okay, I need a data structure can represent the ownership of the pool of money by different owners. So So let's say that each pool has members, and each member owes some amount of units, and anyone can distribute money through this pool of money to its members, and these distributions can be kind of instant or as flows, and members' share of the distribution are proportional to kind of a number of units relative to others, right? So this is a mental model of the data structure. Let's just define it, okay? We have this kind of basic data structure we defined a few slides ago. Now we just wrap it into on the left side, two different new data structure, right? So you say the pool has total units, and you contain a wrapped information. That wrapped particle is actually measured per unit. And then you have each member. Each member say how many units I own, and where is the settled number I have there, and what's my synchronized position of that. Now you have two data structure, and essentially done. You have now a 1 to n. How, right? So again, you need to define this function that we defined for the basic data structure. Now we define what's a real-time balance for this function, right? It's also very, very concise. This is a kind of hallmark of functional programming, right? So you just define pure functions, define data structure, define really, really small functions, and you gradually build things up and you'll get what you want, right? So as you can see here, the real-time balance function for that pool is essentially a few lines, right? You say, I need to see the difference between the wrapped one and the synced one. You multiply by the number of units this member has, and you plus this so-called settled value. Done. How do you come up with this formula? It takes a little bit of time, but once you get it, it's short and it works. But how do you know it works? Right, there's something called a settle also, but let's move on. How do you know it works? Remember, we talked about laws, right? So in order to know if it works, you basically test with the same law we talked about there to see if these new functions you created satisfy those laws. And the good news is they satisfy, right? So now you know you created something new and they satisfy the same law and they work, right? That's the good news about that's kind of why you should do functional programming, because then you just create data, create function, test with laws. And step by step and build things up. And yeah, I'm hand waving here, right? Just trust me, it worked. Right, so now, not finished yet. Now we have data structure. Now we need to go to something finally, right? So we're building the token, right? We're not there yet. Step 5. 5 minutes. All right, so we need a shift and flow, right? So we need to shift the value from two parties, from left to right, and we need to flow money from left to right, right? So that's called two primitives. And in Solidity, I have to do twice this for different data structure. On the left side is two basic particle. On the right side on the right side you have a basic particle is A, and you have a pool which is B. And as you can see, they are very, very similar functions looking, right? So the body of the function is very, very similar. Almost identical, right? It's not a coincidence. Let's see another example. Right, then you have a shift flow, right? They are almost the same. They are just different input types, A and B. They are just slightly different type signature. But the structure of the function is almost identical, right? So this is something that in Solidity they are going to be introducing, as far as I heard from last year. They're going to introduce something called generic programming. So that means when Solidity have generic programming, I don't have to create the same function twice because they are essentially the same. What we need is generic programming so that I can write one function and they can work for both different types, because you can just duct tape it, right? Duct type it. Like in JavaScript, you don't care about the type of it. You just say, if you're a function, it just works, right? So we need a similar thing kind of in Solidity, right? Then we don't need to create the function twice, right? Okay, so now we have laws for the new function, right? So in Solidity, I want to show you one trick in Foundry, rather. Solidity and Foundry. So I have a generator function. So it takes two functions as a pointer as an input, and I can generate tests based on the operation 1 and operation 2. They are abstract function. They are function pointers, and this is kind of my template to generate more tests. What do I do? Right, I use that generator function to create 4 different set of test cases. I say it's a shifting, flow, shift, flow. I've now all the combinations with the generator function, right? So this is something that you could also do in Solidity with function pointers, and then you generate a bunch of the tests using that, right? So, all right, now where are we now? We can do shift, we can do flow, and if you shift from two basic data structure, you get a transfer, isotonic transfer, and you get a one-to-one flow. And if you do the shift for the basic data structure and the pool, then you get one-to-n, both the instant one and both the stream one, right? So as you can see, it's using functional programming to build stuff from bottom to up. You have basic data structure, you have a complex data structure, but same function, and you get you get all the function you need. All right, so you get a functionality you need, right? So, okay, now what, right? So we have a library, pure function library, does a lot of things, but also at the same time nothing, because it can't really change storage, can't do anything. So like, what do we do now, right? So let's call it the infamous M word. If you know function programming, that's kind of the most dreaded word because no one can explain it, right? So but let's focus what do we need. We need a reusable code that use the library we just created to build these tokens, right? So all right, I'm gonna fast track. Sorry if I kind of have to jump a little bit, right? So let's go straight here, right? So what we can do is we create an abstract function, has a function that say I want to flow. I call these pure functions, and then I want to actually modify the storage, right? That means I have to define a virtual function and then do all the tricks, right? So this how you create a kind of reusable code for using those functional pure functions. And well, the implementation in the token. So this is now the final code. In the token.flow, you will see, okay, I use, the only important part is almost in the end, like underscore do flow, and then you have it. All right, so there's another trick. Unfortunately, I can't show it here, but just see, this is actually Solidity code. You can see the last line, right? You have the dot set, sorry, this one. The last part is, this is almost exotic code is like you can do shift and dot flow. It's like a chain of function calls, right? So it's a re-implement the same token flow with a slightly different ergonomics how you do it, right? So what do we have achieved? So we now have a Solidity pure function library for implementing the token. Now we have two variants of the interface that for reusing that code and. Right, why it matters. I'm gonna jump real quick because people are waiting. And so what is function programming? It's really about implement as much code as possible using data definitions, equations, and logical formulas. And to make code actually useful, I need to have the kind of computation strategies stuff, right? So why it matters, I suggest you look at this paper called Why Functional Program Matters. It's really, really old paper. It's 10-pager and it tells you why it really matters, right? So the keywords is that it's for better debugging, reusability, and less maintenance costs, right? The main point I want to actually bring out is that with this with this kind of way of building stuff, you can actually make the form verification really easy, right? Then you can have the, in the Certora, you can have this, define the rule. We say this property we were using Foundry to prove, it always works, not only with 1,000 data samples, but also mathematically always works. There's another magic from Certora is that it can inductively prove that something always works throughout the state of the program, right? Okay, so I'm rushing a lot here, but thank you for listening. Yeah.